actually.
Is it starting?
Yep.
Good. Welcome people who are not here. We are beginning, or have already begun, our unit on so-called applications of differentiation. So last unit was learning how to differentiate everything. Now is using that to solve problems. And we have already seen the how we can solve like related rates problems with differentiation. Now there's like another kind of problem that is more sort of math specific, but has like obvious implications for other things. Well, suppose you have some function, right? Oh, and I'll say that some years this just comes up naturally somewhere halfway through the derivative unit, but I don't think it did this year. Or at least if you thought of it, no one said it out loud to my memory, which is, you know how there's all these problems in the homework where they keep asking you like, hey, find all the places where the function has a horizontal tangent line. That's a question that they keep like asking over and over again, yeah?
Yeah.
And even on the test that happened too. So what's so significant about there being a horizontal tangent line? Why should I care about that so much? Maybe. Yeah, no.
The slope is 0.
So the slope is 0, so what? Killian.
It could be like changing or like could be going from negative to positive.
That was a little bit vague. More to the point, yeah.
The derivative is changing signs.
You guys are just saying words, but you're not explaining to me why I should care about when the derivative is 0.
It's like the local maximum or minimum.
Yeah, I mean, just look at the picture, right? We're not doing any high-level theory now. We're just using kind of like just a quick, fast little common sense thing. Oh, Rajeed, you're actually here right now. I didn't realize you were in the room as I was making fun of your camera. It's okay. We've moved on. One day I will move on.
I don't know if that makes it better or worse.
Yeah. Good. Good. I blame myself for not giving you sufficient direction.
No, it's okay. I was
Okay.
like not doing well that day.
Good. All right. So yes, says whoever said it. I've already forgotten. I think it was Justin. Look, man, just using just your own eyes. Where do you think is happening when the derivative is 0? Well, it just appears that like when the derivative is 0, I have like a horizontal tangent line. One reason I might be interested in that is because it tells me like where my function is like minimum or maximum. And so now, suddenly, we should be able to like do this now, right? This is one of these big math things that we have never been able to do. All through pre-calc A, pre-calc B, pre-calc C, we graphed cubics, but we were never able to calculate where those things were maximum and minimum. Remember how I kept saying, oh, it's just a sketch because we're just gonna like draw some crap and just hope for the best. Well, now we should be able to do it, yes?
What? Does that like not work for like ones that go like?
Yeah, okay, she's like doing a lot of like thinking and stuff. Let's not think yet. That was just gonna throw that out there. But you're totally right. You're totally right, Bradley.
Yeah.
All right, so, and if this function is some important function that you actually care about, you know, a function which tells you like profit or something like that, or maybe like happiness. And maybe this is like number of puppies. And you know, maybe there's like a relationship between the number of puppies you have and your happiness. But maybe like this is like already like 9 puppies. Like that's too much, man. So maybe I would like to know exactly how many puppies I should have to achieve a peak happiness. And that might be, you know, 2.7 puppies.
That's like 0 happiness. That is 0 happiness.
I couldn't resist. Okay, good. Okay, good. Can I get that black marker? I think it's better. All right. So the entire we gotta go like faster. We gotta go like fast. The entire goal of today is everything we're going to be doing for the next hour is finding extrema. I need to find out where functions are big and where are they small, maxima and minima of a function. Okay, in order to do this properly, we should be very, very up to date on all of like our precise definitions and vocabulary of these things, which you learned last year in Pre-Calc A. But I suspect that you do not remember, because this was done for like a couple of days in like October of like last school year or whatever. So like that was like 16 months ago. So first we will do some pre-calculus review. Are you ready?
Yes.
Good. Okay. If you have a function, maybe that looks something like this, say, and let's call this point over here A, and this point over here B. Then I would like to be able to like talk about this function to say where it has a max and where it has a min. Let's call this point where there's a max over here. Let's call this C. Let's have a point where let's call this D. And good. And let's let this function be f. Well, all right. What is, just off the top of your head, what is the maximum of this function f on the interval a, b? Good. Yeah, and you guys are all giving the correct answer. Just to the answer is f of c. To clarify, when someone asks for the maximum of a function, they are asking for the maximum y value. Though the maximum is happening near x equals c, the answer we always give to this question is specifically the y value. And that y value is up here, it's f of c. Cool? Say cool. Cool. Some people have other names for this thing. Some people call this the global maximum. Or some people call it the absolute maximum. Did Kirk use those words?
Yeah.
You're good. So global or absolute. If there's no adjective in front, then sometimes that's what we mean, absolute or global max. Okay, what is the minimum of f on the interval AB? It is f of a, according to the picture, yeah. Woo! Good. Okay, so I would like a definition of this. So let's just sort of draw a function or whatever, and let's take some point C, and let's suppose the function looks like this rather. And okay, I would like to know what does it mean for a function, what does it mean for f of c to be the local max? So let's just start. Definition, f of c is the absolute or global max of the function f on the interval, and I'll fix this interval to be this particular interval, a, b, if and only if what? Just using common sense, what do we really mean when we say that f of c is the absolute max? Everyone, out loud.
So like for all values.
For all values of x.
It's the biggest one. It's just the biggest y value. That's all, right? And so for it to be the biggest y value, what we should say is that for all x on that interval AB, I'm realizing I want to change this slightly. Sorry. So hold on. Note that Note that my definition is always relative to some particular interval. Because in calculus, we want to talk about not just the maximum, like sort of in general, but the max on some particular interval. But this definition I want to give right now, I want it to be totally general. In other words, I want this definition to apply not just to closed intervals, but also to open intervals, also from like negative infinity to infinity, whatever. So I'm going to be kind of fancy now, and I'm just going to say I. For like I is some generic interval. F of c is the absolute maximum of f on some interval I, if and only if, for all x on that interval, well then f of x is less than or equal to f of c. Cool. And notice that I need to say less than or equal to, because c is itself one of the x values on that interval, right? So that's just the smoothest way to say it. Okay, good. So that is just like a pre-calc definition. Now we're going to look at some examples. Ready? I'm going to draw 9 pictures.
Do I need to move?
And at some point, the camera should get moved, I guess. And then we'll do some little ones over here. Okay, so so here is a function. It looks like this. And let's let this be A, and let this be B over here. So, okay, and this is A. All right, good. Now I have some questions for you. What is the maximum of this function f on the closed interval AB?
B. F of B.
Careful. F of B, right? It's always a y value. The maximum, the answer to the question, what is the maximum, is always a y value. And yeah, it does appear that f of b is the largest y value. Now, notice that this function, the way I've drawn it, seems to be going on up and up and up. But I'm only asking about the function on this very particular interval. And if I'm only asking about the function on this very particular interval, then only what the function is doing on that interval is relevant. So I might very well just erase the function elsewhere, because it's like irrelevant. Cool? Okay, and so good. What is the minimum of f on the interval AB?
A.
Adam.
F of A.
F of A. Good. Woo. Okay, now I will draw what is supposed to be sort of the same function, but I'm going to ask now a different question about this function. What is the maximum of f on the interval A, B open? Like that.
Wait, that's like not answerable. No. Yeah, you can't answer it.
Some people are freaking out, some people are mumbling, some people are mentioning limits, other people are saying, refusing to answer the question. Okay, notice that if I'm asking about the function on the interval from A to B, excluding the point B itself, then I might very well just erase the function outside that interval, because what the function is doing outside that interval is irrelevant. And now that I draw it like this, now are you sort of feeling that maybe Bracken's got a point, right? She said unanswerable. You have something to say?
Oh no, I was not going to say that.
Oh,
I was gonna
Bracken, what's your thought process?
So like so the maximum would be like f of b, right? But you don't have that specific value, so you go to like infinitely less than it. But like the things you can't go infinitely less than. That's just like not a thing you can say.
Yeah.
Provide a counterpoint.
Bracken is saying, and then yes, Bracken is saying that if you get really, really, really close to b, then the values of my function just get bigger and bigger and bigger and bigger, but like they never quite stop, and they always get a tiny bit bigger. Counterpoint.
Limits, like you don't need the point at the limit. So it
Good.
can be like the
Yes.
limit of
So
f
this
of
is
x.
what Rajiv was saying also. You're trying to like get limits involved or something. So you're really just trying to finesse it a little bit or something. Like, oh, it's like the limit as x approaches
like
b
f
from
of
the
b is
left.
not
But
relevant.
what is the limit as x approaches b?
F of b.
It just is f of b, right? A limit is a number. But of course, f of b is the wrong answer, right? To this question. Because f of b is simply not a y value that this function obtains on this interval. And so the true answer is, I think what she
I
said,
see.
which is right, that the y values keep getting bigger and bigger and bigger and bigger and bigger and bigger, but they just never stop getting bigger. And so the answer to this is that there just is no maximum of this function on this interval. This is not so different from just like, take like the interval of all real numbers between like 1 and 4, right? So what can you say about the set of all real numbers between 1 and 4? What is the largest real number in that interval?
You don't even know.
Well, once again, there just is no largest real number, right? Because whatever the closest number, whatever the biggest number is you can think of, like 3.99, I can always just add another 9, man, and then I'm always a little bit bigger than your number and closer to 4. Cool?
Yeah.
Okay, so good. So that's like a thing that sometimes happens. Okay, we gotta go like fast now. What's this? Is the function? It's like kind of boring. What's the max of this function on the interval from negative infinity to infinity?
It's C.
Jones
C.
messed it up.
Oh, wait, yeah, F of C.
This is just, let's just let this be like a chill, like a quartic, like an upside down quartic. So then I think Noam is right? The answer is f of c. This is just to say that we certainly can ask about the interval that we take a look at can be the entire real number line. That's a legit thing. Okay, I got another sort of slightly subtle issue. What if I take the sine function, and okay, we all know what that looks like. It looks like that or whatever. So now I'll ask the question, what is the max of the sine function on the interval from negative infinity to infinity?
Can you do that?
What's wrong?
No, it matches our definition.
It matches our definition.
Well, I didn't even hear an answer yet. What's an answer?
Pi over 2 plus. Oh, wait, no,
One.
I'm saying x value. It's 1.
One.
Okay, Brackett is
Pi over
insisting
two,
that the
one.
answer is 1. And yeah, I think she is just right about this, right? Right, so yeah, don't get all freaked out about weird things, right? This function hits that high point infinitely many times. But that's not what we're talking about, right? The question we are asking is, what is the largest y value? And the largest y value just simply is 1. This function obtains that largest y value infinitely often. Cool? Good. And like the natural extension of this is, what if I just gave you like a constant function, just like the line y equals 2? What is the max of this function on the interval from 1 to 7? Just 2, right? The max is just the largest y value. Okay, good. Okay, I got some other things we could do. What about if there's some sort of volcano action? And so here's A, here's B, and let's suppose near the middle of the volcano, things are getting really huge. But I want this function to be defined everywhere. So suppose I define the function at C to be like 3. Okay, question. What is the maximum of f on the interval AB?
It's infinity, it doesn't exist.
Yeah, there is just none, man. This function, once again, does not have a maximum because there is no largest y value that this function obtains. Because when I get very, very close to C, this function just goes big, 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 big up. Cool? You have a question?
In limits, we said that we set infinity to show how it was undefined. Should we say
Sure.
that here? Can we say that here or no?
No one does that because it literally is a y value. In this part is this, so there's no y value, so you don't want to answer infinity. Okay. La 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 la. 2 more, 3 more. What if you have a function which is just kind of like chilling up towards some sort of asymptote? So here's like k, and here's a, and the function's just kind of doing that. Yeah. So now, So what is the max of f on the interval from a to infinity? All right, someone just yawned out the answer, then it does not exist. Again, now for slightly different reasons, right? It's no longer the case that the values are getting infinite, but what is happening to the values? They're just getting a tiny bit bigger. This function is bounded, it never goes above k, yet as x goes out to infinity, it just gets a little bit bigger. So again, there's no largest y value. Okay, cool. Then there's like another kind of example where like some weird stuff can happen where like maybe you go like rump, and then there's like a jump, and then you get something like that. Oh yeah. Whoa. Classic everyday function. So here there's like this jump, right? All right, so question. What is the max of f on the interval AB? Yeah, I think once again, it does not exist because there's no largest y value because the closer you get to C from the left, the bigger this function gets, but there's no biggest one. Okay, and we don't need this math picture. All right, good. So, looking at these 8 examples, is there can we discern some sort of pattern? In some kind of a way, or more specifically, when does it appear that we can be confident that there is a maximum? And when does it appear that there might, under what conditions can we not conclude that there's a maximum? Give me one.
It's unbound and continuous.
But don't try to do it all in one answer. Just give me one sort of property that seems worth discussing. Continuity. Yeah, continuity seems to be a key property, right? Here we have a function which is discontinuous in the infinite style, no max. Here we have a function which is discontinuous in the not infinite style, but it's still enough to cause me to there to be no largest y value. Okay, so it seems like continuity is something important. Okay, but that's not the whole story, right? Because this function's continuous, this function's continuous, and yet there is no max. Yeah, Philip.
I think because they have there's an open interval, and so that should be closed to have a max.
Philip is focusing on the sort of openness of the interval under discussion as being also relevant. And I think he's exactly right. What Philip is saying is, look man, even if you give me a continuous function, if you search for a maximum on an interval that is even partly open, you're going to have a bad time, right? Maybe. And over here as well, right? We consider infinity to be kind of an open interval. All right, so in fact, those are exactly the two key features. And so we have a theorem. This theorem is called the extreme value theorem.
That's pretty
And
extreme.
yeah, the extreme value theorem says that if I have a function which is continuous on a closed interval, then this function will have a maximum. I'll write this down. If f is continuous on the closed interval AB, then f has an absolute max on AB and an absolute min on AB. Okay. So, right. This is a very sort of simple theorem, which is extremely obviously true, which means that the proof is going to be really, really hard. And so we are not going to do the proof. It is too hard. It is not even in the appendix. It is one of those theorems like the intermediate value theorem, which requires like fancy properties of the real numbers that we don't know anything about yet. But I want you to at least like feel that it should be true. And I would like you to at least feel why each of the pieces of the thing is sort of necessary. And okay, so let's do these kind of one at a time. Look, let's just think about, so there are two things which we're insisting upon. One, we're insisting upon continuity. And two, we're insisting upon that we are looking for extrema on a closed interval. And like, the reason why it's sort of obvious that there must be a max can be seen by just trying to draw a continuous function on a closed interval and sort of just see what happens, right? So take a closed interval a, b. I'm going to draw three pictures now. And this is a kind of a casual conversation because this is not a proof. It's just a thinking about why it must be true. Well, like here I am, right? My function is continuous. Well, just telling me that my function is continuous already like imposes a quite strict amount of behavior on what this function can do. No crazy jumps, no crazy oscillations, no infinite behavior, nothing weird like that, right? All it can do is just go from here to here in some kind of a manner. And so if you think about what this function could do, one thing it could do is just kind of like go up like that, right? Let's say. In this case, what's the absolute maximum? F of b, the right endpoint. And the absolute minimum is f of a, the left endpoint. Okay, but the endpoints don't have to be the maxima, because instead, maybe the function might do something like, whoa. Now, where is the minimum?
That hump down.
This point's down here, right? Whatever that is. And of course, it could be once again, I still have to get from here to here, and I can only do it in a continuous fashion. But it might be that like neither the max or the min is the endpoints. Yeah, so it could be that that's the minimum and that's the maximum. Okay, and I guess the last thing to mention is why do we insist upon continuity? Well, let's just point to one of these pictures. Like, which is why do we insist upon continuity? Why must we insist upon continuity to ensure that there is a maximum?
Because there could not be.
Like, for example, which picture?
2.
This one. They're not numbered, but yeah, this is the classic example of why we need to insist upon the interval being. No, not 2.
What?
This one. Are you calling this 2? No. This is a good example of, even though we are looking at a closed interval, this function is not continuous, and so there's no maximum.
Oh, yeah.
Here also, this function is not continuous, so there's no maximum. Why do we insist on the interval being closed? This reason. Everyone cool?
Yeah.
Right. So that shows why we really do need both of those things. Okay, good. And the sort of final thing to kind of note is well, okay, the whole goal for today, as I said, was to find extrema, right? So where, in general, if I have a function which is continuous, and I am looking on a closed interval, so I know there is a max and there is a min, where should I look? This is a very sort of silly question. This is a very sort of silly question. I'll just answer my own question because it's too vague to be answerable by people. I should look at the endpoints because the maximum and minimum might be there, and the other place to look is everywhere else in the middle. Okay, and so basically, what I should do if I'm searching for the minimum and maximum, I should look at the endpoints, and I should look for all these relative minima and relative maxima. All right, so the problem now shifts to how do I find relative minima and relative maxima? Okay, and now you guys are all trying to answer the question, which is that it has something to do with the derivative, and you are right. But first, let's just review even, like, what is a relative maximum? This is another thing we learned back in pre-calc, but we need to have a sort of a good definition of it. Okay. This is a function, and this point C we call a relative max. This point, good, stop talking, good. This is the relative maximum. Note that this relative maximum is not the absolute maximum. So, all right, give me a definition. F of C is a relative or local maximum for the function f, if and only if what? Wait, no, don't give me any derivative stuff because we want a definition. The definition should be a pre-calculus definition. Follow? Also, concatenates the board. Yo.
If an interval exists, such
Okay, wait. So Svelana's giving us the fancy version. First, can we get the baby talk version? What does it mean to say that this is a relative max?
Stuff to its left and the stuff to its right is all less than it.
The stuff nearby. Good. Yes, it is a relative max if it is the biggest relative to the nearby points. What's all the relative maxes? All that, yep. A number is a relative max if it's the biggest relative to the nearby points. And Svelana has remembered, or maybe she's just coming up with it on the spot, the sort of formal definition from pre-calc A, which is we insist that there be some sort of neighborhood around C, some open interval. And what we want to be true is that for all the points in that interval, when I plug them into the function, f of c is the biggest. Okay, so here we go. F is a relative maximum for f, if and only if there exists, I'll just use words, there exists an open interval, and I call that open interval AB, containing the point C, containing C. In other words, the point C is on the interval AB, or you could say it more simply as just like that. Just kind of like restating the same thing in 3 different ways. Such that, so what should be true about this open interval? Well, I'll let you finish now.
F of C is the greatest on that interval.
f of c is the greatest on that interval. So that if you take any x value in that interval AB, yep, f of x is less than or equal to f of c. And again, I want to use less than or equal to because fc is itself a point in that interval. No.
It's not like really similar to the extreme value theorem. It's like it's on an interval too. It's like the max.
I don't know exactly what you're talking about. This is just a definite, I mean, okay, I guess, yo.
Why does it have to be an open interval?
Why does it have to be an open interval? We specifically insist that it be an open interval because we want to reserve the relative maximum to be like actually talking about the function, not the interval that you're asking about. Okay, so this is the very next point I was going to bring up. If you have some function that just like abruptly ends here because it just does, then this is like not a relative maximum. And it's not a relative maximum because our definition like specifically excludes it. The insistence upon an open interval is basically that's built into the definition because I don't want to call these relative maxima.
Oh.
And the reason why I don't want to call these relative maxima is because this is kind of like the maximum like by accident or something, right? It's because like this is the maximum because I happen to just stop looking at the function there. Versus this being like some sort of intrinsic property of the function that it has a maximum. Follow? Okay, good. Yes?
What's the difference between a relative maxima on an interval and a global maxima on an interval?
Oh my god, this is what we've just been reviewing for the last 45 minutes! The absolute maximum is the biggest y value. A relative maximum of a function, anywhere, is a place where it's bigger than the nearby points.
But you just think that's kind of interval there.
No, I think you're missing this. This, for example, is the absolute maximum of this function on this interval. It's the largest y value.
Yeah.
But this is not a relative maximum. Now, a relative maximum can also be the absolute maximum. For example, this point, f of c, is the absolute maximum, but also it's a relative maximum because it's bigger than the points nearby. Follow?
Yeah.
This was like the whole point of, okay, good. I will make one more comment, which is this way of phrasing it is like less common. The more common way of phrasing it is to say that f has a relative max at x equals c. When you say it this way, then you're just telling everyone that the relative maximum is going to occur at the point C without specifically saying what the relative maximum is. Okay, are we good?
Yeah.
This was so far like almost all of this was just pre-calc review, just with the extreme value theorem thrown in. All right, so now we have to do some calculus. The goal is to find extrema. The immediate goal is to find relative extrema, because we know that if we combine that with checking endpoints, that'll be all of them. All right, well, now finally you people have been saying it over and over again all period. Let it all out. Where should I find relative extrema? No, relative extrema. Relative extrema. Where should I find relative extrema? When you have a horizontal tangent line, blah, 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 derivative is 0, blah, 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 blah. Yes, it appears